So the next item is counters. We are going to take a look at uh, how we build them, what they need to do, and see if we can use a JK flip-flop to in fact design a counter. Not a very good one, but maybe we can get a basic counter working using a JK flip-flop. So let's try to do that. So what does it do? What does it need to do? Purpose. So the purpose of a counter is, believe it or not, to count. So how do I count in binary? How does the count happen in binary? Because these are all binary components, meaning their outputs can be 0, 1, 0, 1, 0, 1. So to look at counting in binary, we look at the conversion between binary and decimal. And we are looking at decimal because everybody is familiar with this number system from a very early age. We know how to count in decimal. Everybody has 10 fingers, 10 toes. So that's a very familiar number system to humans, the decimal number system. And now we have something that should allow us to count in binary. So we are going to see how binary numbers convert to digital, uh, the decimal numbers. So just so I have the audio set up correctly. Are you guys able to hear me all right? Okay. So let's see. Binary, what is the least value that I can have in binary? Well, I have 0 in binary. But if you have 0 in binary, you have 0 in decimal. Now let's start writing a few numbers in binary. I have 0, I have 1 then, and then I have 1 0, 1 1, and 1 0 0, 1 0 1, 1 1 0, 1 1 1, and so on. And notice how I'm writing this. I'm writing this sequence in the same pattern I wrote the truth tables. So the least significant or the rightmost position toggles 0 1 0 1 0 1 0 1 and so on. And the next level to that goes 0 0 1 1 0 0 1 1 and so on. And the next level to that goes 4 zeros and 4 ones. So that's exactly how you would count in binary. So what does that convert to in the decimal number system? So for example, if we do this for say 101, well, this is a binary number system. So the weight for each digit is 2 raised to 0, 2 raised to 1, and 2 raised to 2. Why is that? Why is it 2? Because it is a binary number system and there are only two possibilities for any number, 0 and 1. And the power of that 2 goes from 0 to 1 to 2 and it keeps increasing as we have bits, more and more binary bits on the left. And I'll try to relate this to a decimal number system so that you guys can clearly see that. Say we have 386. How do we write 386? We do the same thing, 10 raised to 0. We multiply 8 with 10 raised to 1. We multiply 3 with 10 raised to 2. And then we add all those results up to get 386. So now to convert 101 to a decimal number system, we are going to multiply 1 with 2 raised to 0, and we are going to add that to 0 times 2 raised to 1, add that to 2 raised to 2 times, well, let's follow the same pattern. 1 times 2 raised to 2. And those are 2 raised to 2, 2 raised to 1, 2 raised to 0. Those are going over there. That's the weight of that bit. Similarly, the same reason why we had that increasing powers of 10, and then they get scaled or weighted based on the bit. 101 is going to be 1 there, 0 there, 1 there. So if you add all of that up, you are essentially going to get 5. So if I do this for all these numbers, and I'm claiming that I'm counting in binary on the left side, you might imagine what should happen on the right side. It should simply increase as 0, 1, 2, 3, 4, 5. We did that just now, 6 and 7. So this is showing you a conversion between a binary number system to a decimal number system. And what we have written is the output of a 3-bit counter. So that is the output of a 3-bit up counter. It is counting up from 0 to 7 as opposed to counting down from 7 to 0. And it is only 3-bit because the options are 000 all the way to 111, and we are writing up here, or we have in the counter all the 8 possibilities between the 3 bits. So that's what we desire. We need a component, we need a digital device that gives us a 3-bit output which can go from 000 all the way to 111, and it should do that at a particular speed, right? So it should respond to perhaps a clock signal, and every time it sees an edge, maybe a negative edge on the clock, it goes up 1 value in this count. So that's what the counters are. That's the objective, and that's what they should be doing. Now, in JK flip-flop, when we were talking about JK flip-flop, we were referring to the output as Q. However, over here, we have 3 outputs. We have an output for the least significant bit, and we have an output for the bit to the left of that, and we have an output for the most significant bit. So instead of using Q, I will, for a 3-bit counter, I can make them Q2, Q1, and Q0. So I can use Q0 for the rightmost bit or the least significant bit. I can use Q2 for the most significant bit. And this is of course for the 3-bit counter. As you have more and more bits, your Q2, Q3, you will have more and more value or indices for Q. So for example, if you had a 4-bit counter, you would probably have Q3, Q2, Q1, and Q0. And that 0, 1, 2, 3 indicates the importance of that particular output. So 0 is least significant. So that means it changes the fastest. And as you move to the left, the frequency always keeps getting divided by 2. That's a counter. And let's try to explore that in this experiment 7. So what I'm going to do is I'm going to pull up give me 1 second here. So I've got, let's see, homepage, experiment 7, and I try to go to that right there. Actually, I will not be able to write on it. So Right. So while I set this up, if you guys have any questions, you should ask. Uh, all right. So figure C-1 claims that this is a 3-bit counter, 3-bit up counter. Now, this particular figure here shows 3 JK flip-flops. The claim is that it is a 3-bit counter, and we have actually looked at what the JK flip-flops do, the 4 different states of the JK flip-flop. We have looked at that. So let's try to see if what we have learned about JK flip-flop actually makes sense for the 3-bit counter. We are going to assume that uh, each of these JK flip-flops is a negative edge triggered JK flip-flop. We are going to assume that. So if we do that, let's see. There is a count signal that is in the input of the clock for the first flip-flop, and then the output of each flip-flop actually controls the clock on the next guy. And all J's and K's are connected to an input called count enable. So let's say if I want to enable the counter, I would start with count enable, and I would set that to 1 because I want this to count. And if I set this to 1, all my flip-flops are going to be in the toggle state because all J's and K's are 1. So all 3 flip-flops are right now in the toggle state. And as count is going up, so this signal, let's say I have count that goes 0, 1, 0, 1, 0, 1, and so on. And let's call this particular point, say Q0, and this one Q1, and say this one is Q2. So if I assume that this is count, and I have made sure that I have enabled the counter, so count enable is set to 1, what is going to happen at Q0? Well, because we know the nature of the flip-flops, every flip-flop is in the toggle state. So every time there is and we are assuming that these are negative edge triggered JK flip-flops. So what is going to happen? As we see a negative edge on the count signal, we are going to have a toggling effect on Q0. And just to make our lives a little bit simple, we are going to assume that we have a starting Q0 of 0. So I can use the clear input and make all the outputs to low. So let's see if I can do that. So if my Q0 is starting at low and the first flip-flop is in the toggle state, so when it sees the first negative edge of count, it is going to flip to a 1. So that's the time it sees the first negative edge, it is going to flip to 1 at that moment. Next negative edge, it is going to again toggle to 0. Next negative edge, it is again going to toggle to 1. Next negative edge, it is going to toggle to 0. And these transitions happen slightly after. So maybe I can simply take this and sort of move it to the right a little bit, not too much. because they happens just after that edge. So that's Q0. Now what is going to happen to Q1? Well, Q1 is responding to the negative edge of Q0. The same thing that we used for count, now we are going to use Q0 and Q1 to do the same thing. So I can sketch Q1. Let me, oh my gosh, sorry about that. Q1. So I'm going to set up Q1. Okay, so let's set up Q1, start with 0. And I'm going to toggle at every time I see a negative edge on Q0. So I've got a negative edge of Q0 over here. If I start with 0, I'm going to flip soon after that, and I have another negative edge over there. So soon after that, I'm going to toggle again. And I can apply the same logic to get Q2, which is going to toggle every time Q1 goes from high to low. So I can use, say, a different color to write Q2, assuming that it starts at 0. Every time I have a negative edge, it is going to toggle. And this is going to keep continuing. So notice what is happening here. Let me use green to indicate the levels of Q0, Q1, Q2. So over here I have all of them 0. Next I have that. Next I have 0, 1, 0. Next I have 1, 1, 0. Next I have 0, 0, 1, and so on. So if you look at the decimal values of this, 0, 0, 0 is 0. So for the first few seconds, or until the first negative edge of the count, our counter was counting 0, then 1, then 2, then 3, then 4, and so on. So by connecting the 3 flip-flops back to back and driving the clock inputs by using the output from the previous state and setting all the flip-flops in the toggle state, I'm able to design a counter, and this is a asynchronous counter. And it's called asynchronous counter because the count signal is not synced with all the flip-flops. It is only controlling the first flip-flop. So each flip-flop is synchronized with respect to the output of the previous one. So that's an asynchronous flip-flop. And one big problem with this type of counter is because things are going to change slightly after the negative edge in the previous one, the count is not going to increase in a straightforward manner, as in it will not go 0, 1, 2, 3, 4. During that transition period, you may have what we call transition counts. So it might, from instead of going from 0 to 1, it might actually go from 0 to 2 to 3 to 1. So in a very short duration, it might switch a few states because the response is slow, because they are not synced with the same count signal. So transition counts is a negative. It's a disadvantage of having counters set up this way. Okay, so that's a quick discussion on counters. Over here in this table, we have uh, a conversion between binary, decimal, hex, and octal number system. Um, we can talk about more about the hex and octal conversions, perhaps not today, but maybe at a later time. But we have right now seen how to do the conversion between binary and decimal at least. Okay, so let's stop a video here, set up the counter. Why do we need a counter? If I look at the experiment here, figure C3 is a simulation. So that's okay. You guys will be able to do that. But figure C4 is actually a 4-bit counter. and it is 4-bit because, as you can see, there is a QA, QB, QC, QD indicating the 4 output bits of the counter. We are going to use the 74393 chip to do this 4-bit counting exercise, and it turns out that it is actually a negative edge triggered 4-bit counter because of the bubble. And to convert this into a positive edge triggered counter, we simply use a NOT gate in front of it. So if the input that is coming from the analog, AWG, so that's the arbitrary waveform generator from the oscilloscope, as from the analog discovery, if that is going low, high, low, high, over here things would go high, low, high, low. So if it is negative edge triggered over here, because of this, it is going to effectively function as a positive edge triggered 4-bit counter. So we'll take a look at the experiment corresponding to this in a few minutes. Right now, time is 9:13. Let's come back at say 9:20. So we have a 7-minute break, and we come back at 9:20 to do the experiment on counters, 4-bit counters. So we look at figure C-4.